So, except for the fact that we have to see if Nicomachus' theorem can be generalized. But the answer is very easy. Unfortunately, no, it cannot be generalized. If you try with different powers, you will see that the equality does not hold. So what is left to see now? What remains to be seen in general is how these quantities behave. That is, the sum of the first k numbers raised to the power of p, or the sum of the first k powers, to see if there is equality, what it consists of, and how they can be calculated. Well, in the case of the first k numbers raised to the power of p, it is very simple. Thanks to Gauss's sum, we just need to raise Gauss's sum to the power of p. As for the sum of the first pth powers, always remembering that p is a positive integer greater than 1. This is, let's say, the scope in which we are working. We can perform this operation as usual. The usual technique, we add and subtract the integral, in one case expressed over the entire interval 0n, in the other case expressed as a summation of the integrals over the individual small intervals. And the integral between 0 and n can be solved as an immediate integral. And then we have this expression. If we calculate it, we arrive here, and we have to expand this binomial. This binomial can be done. It can be expanded relatively easily with Bernoulli. Here, let's say we need to perform this multiplication. We have the binomial coefficient, which I have written here in the form of factorials, and we need to substitute this into this formula. So let's start calculating. P plus 1 is the denominator. When I bring k raised to p to the numerator, I will have k raised to p multiplying p plus 1, and I generate these first two terms. Then I have minus k raised to p plus 1, which comes from this with the minus sign, and then all the terms of the binomial with the positive sign, let's say, in front. And let's start looking at these binomial terms starting from the lowest powers, so or rather from the highest powers. K raised to p plus 1 minus p, these two terms, minus p plus 1 in parentheses, times k raised to p plus other terms. I didn't write the other terms because we don't need them at the moment. I wrote the last term, it's a minus 1, because we see that in this summation, thanks to this term here. The minus 1 term is sometimes there, sometimes it becomes 1, depending on the power p, if p is even or odd, actually if p plus 1 is even or odd. Anyway, the important thing is that we have a series of simplifications, because the pk that originates from this term cancels out with the second term of the binomial series expansion. And then we have kp, which also cancels out with the second term, and then we have the first term, which cancels out with this term here. So we have a series of simplifications. In the end, what do we get? We arrive at this specific formula where the summation process stops at p minus 1. So in essence, it is exactly the same structure as we had before, but it concludes a bit earlier than the previous version did. The term p plus 1 can be pulled out of the expression. And similarly, the factor that was originally in the denominator can also be pulled out. And so after simplifying everything, in the end, we are left with these two distinct summations that we need to evaluate. However, if we look at the index k, we see that the index k only appears here. So we can also swap the summations, bring the k inside, the summation over k inside, and we have this final series that is more this final form that is more interesting because it gives us a recursion. You see that the sum of the powers depends on the sum of the previous powers and stops at p minus 1. For a computer scientist, this already gives the idea of using a recursive formula to calculate this value. Is that okay? And let's therefore make a small program. What do we need to see? That we calculate k raised to p separately first, and then we calculate this formula and see if they really correspond. Since the formula is, let's say, relatively complex, if we implement it correctly, the fact that the numbers come out the same on both sides is already a good indication that this formula is correct. It's not an absolute proof, but it's a good indication. So let's go and look at this program. We can look at this program directly in Python and see how it is structured. We have a function that I called sum of powers. And in this function, I first put the special cases. The cases where, let's say, we don't need to do the calculation, and therefore exponent less than 0, etc., etc. With p equal to 0, it can be verified that we have a special case, but a very simple one. And therefore, the sum of powers gives us the result n. With p equal to 1, we have the Gauss sum. And so I set the result equal to the Gauss sum. With p equal to 2, we have that previous result that we tested during the course of the video, in the initial part of the video. With p greater than 2, we must use this recursive formula, this one, okay? And so we calculate it. Let's go see. First of all, let's start from this sum, which is nothing but this term n raised to p plus 1 divided by p plus 1. This division will be done at the end in the program. You see this division here at the end, therefore. However, we calculated n raised to p plus 1 here as the base, and then the summation begins. So the summation is this. It is the summation with the alternating sign. You can see the alternating sign here. With the binomial coefficient, the binomial coefficient is this, memh, p plus 1 as the binomial coefficient clearly, and you can see it here. And then this sum, exactly this sum here, this sum here is the result of the same function calculated with p minus 1. So it is the recursive result that we can easily use. So here we have this product. We take the product of the three terms and recursively call this function until, by going down with the exponent, we reach p equals 2. And this particular case comes into play. The recursion is resolved, and so on. Here in the main program, in the main part of the script, we can instead calculate p directly the sum of k raised to p. And we do this, in this case, for the power p equals 3. All right? So we use p equals 3, and then we do it for various n equals 1, n equals 2, up to a total of n equals 10. Let's perform this calculation and see what the result is. In the printout, we have first the value of n, then the result of this sum, which is k raised to p, calculated directly, and then the result of this function, which is actually the application of this formula. And we see that it coincides in all cases. So we can say that we have performed a verification, I repeat, it is not an absolute verification, because but a formula that is already quite complex. If it gives a correct result, let's say it can give us enough confidence that this formula is the one we were looking for. So we can conclude the discussion. One last consideration. We have seen that the theorem does not hold for generic p. It is enough to make a counterexample. We won't waste time on this. This equality does not hold either. This equality does not hold. You can see it immediately, because one already has an idea by calculating n times n plus 1 divided by 2 raised to p is not calculating this result. Okay? So let's reflect for a moment on this equality and see what we can say. So, looking around a bit, as usual, it can be seen that in general the result is this. That is, the sum of the powers is less than the power of the Gauss sum, okay? Always keeping np as integers and greater than 1. Pay attention to this value, because later in the conclusion I will say something else. What happens if we substitute in this formula? We consider the simplest cases, n equals 1 or p equals 1. We see that the equality holds in that case. So it holds if I am summing only one number, well, obviously 1, or raised to p for any p greater than 1. It always equals 1, and the same goes for the sum raised to p. So n raised n equals 1 is simple. P equals 1 is the same thing, because we calculate the same, let's say, value on both the right and the left. So we have equality in these cases. In general, however, the inequality holds with k raised to p, sum of k raised to p, less than the sum of Gauss raised to p. How can we see this? For this, let me give a very academic, very simple demonstration. because we calculate the sum of Gauss raised to n, and we know that this second term is equal to the sum of Gauss raised, to p. We know that this second term corresponds to this. Let us attempt to calculate this specific value once again, and this time I would like us to refer back to the figure that I showed you earlier. Please take a moment to look closely at the diagram as we walk through the steps together. So the sum of the powers, of the pth powers of the first n numbers, we can go and see it from the figure, is equal to the histogram. That is, to the areas of these rectangles added together. Okay? And this obviously only applies to certain values of p, but it is a line of reasoning that can be extended in general to all values of p. And if I calculate at this point the area of the rectangle that contains this histogram, how much will this rectangle be worth? Well, on this side we said, even if it's not written on the figure that it's worth n, on this side it's worth n cubed. In the figure in general, n raised to p. So this rectangle, the rectangle that contains the histogram, is worth n times n raised to p. And so let's go see again what we can say. We are here. So k raised to p is equal to the area of the histogram in the figure. This area is certainly smaller than that of the rectangle which has n and n raised to p as sides, which contains the same histogram. And so we have sum of k raised to p is less than n times n raised to p. Now for each of the two terms, we find a further upper bound. We bound n with n to the power of p over 2. We see that this equality holds only when n equals p equals 2. So in general, we write n is less than or equal to n to the power of p over 2 of n to the power of p over 2. N to the power of p is less than n plus 1 to the power of p. So if we go and substitute with even larger terms, so we replace n with n to the power of p over 2. We replace n to the power of p with n1 to the power of p. We certainly have an upper bound because we have the greater than or equal to sign, but here we have the greater than sign. At this point, if we go and look, this is nothing but the Gauss sum raised to the power of p. So in general, we can say that actually here we should have the greater than or equal to sign, okay? Because it holds for p equal to 2. And in general, we can say that with this technique, one can demonstrate what the ratio is between k, the sum of k raised to the power of p, and the Gauss sum instead raised to the power of p. Okay? The very last consideration is that this inequality is very important, but it must be proven when p is actually less than 1, is between 0 and 1. And it takes on a considerable importance in many fields of analysis. And but it is a different case from